Alright, so in our last discussion, we discussed Coulomb's law that gives the force between two charges, and we used Coulomb's law to develop the concept of electric field. So electric field due to a point charge q1 was determined as E equals to 1 by 4 pi epsilon 0 q1 divided by the distance between the observation point and the source charge square and a vector that points from source charge to the observation point. Excuse me. So this is a unit vector. Okay, so that was our electric field, and this unit vector of course can be written as r minus r prime. That should be a prime. Okay, and I guess we don't need that. Okay, r minus r prime divided by the magnitude of r minus r prime. Okay, so this electric field due to q1 can also be rewritten as 1 by 4 pi epsilon 0 q1 stays as it is. This is actually q sub 1 divided by r minus r prime cube times r minus r prime. Alright, so this is due to a single point charge q1. However, if we have collection of multiple point charges, let's say we have q2, we have qn, all the way up to qn, and we are trying to determine the electric field due to n discrete charges. For n point charges, this electric field can be written as 1 divided by 4 pi epsilon 0 q1 r minus r prime cube times r minus r prime. Okay, so we need some changes here because the position vector of q1 is r prime 1. We were okay with r prime in our earlier discussion because we just had a single point charge, but now however we have multiple point charge, so we need to specify the position vector for each point charges. And so for the next point charge q2, it becomes r minus r prime sub 2 cube r minus r prime 2. Okay, and I will simply write dot qn divided by r minus r prime n for the nth point charge. Alright, so now I can combine this into a summation form. By 4 pi epsilon 0 is common, summation I equals to 1 to n, and this becomes q sub I divided by r minus r prime I cube times r minus r prime I. Okay, so this is the electric field due to n point charges due to n, if you want to explain, discrete point charges. That should make more sense. All right, so now if our charges are distributed continuously over some region, if these charges are distributed continuously over a region, the summation becomes an integral. So what I mean is, so the discrete variable now becomes a continuous variable. For discrete variable, we use summation. However, for a continuous variable, we use an integration. That is the difference between summation and integration. So now this electric field can be written as 1 by 4 pi epsilon 0. The summation becomes integration r minus r prime remains as it is. On the denominator I have r minus r prime cube, and instead of q we will have dq. Alright, so now we have three scenarios. So what could be these charge distribution be? So first scenario, let's say we have these charges distributed over a line, and that is called line charge distribution. So charges distributed over a line. Total charge is q. The length of the line, let's say, is L. We will use rho L, which is called as line charge density, or more specific, I should call it as uniform line charge density, meaning that the charges are equally distributed over the length of the line, and that will be q divided by L. Okay, so that means q is rho L times L, and our dq with respect to dl will be simply rho L, and dq therefore will be rho L times dl. Okay, substitute this. Let me give a name for this equation. Let me give as 1. Substitute this to equation 1, and you get your electric field due to a line charge distribution as 1 divided by 4 pi epsilon 0 integral. Okay, I want to write that rho L on the front. Rho L times r minus r prime divided by r minus r prime cubed times dl prime, to denote that this dl denotes the location for our source charges. Okay, similarly, if our charges are distributed over a surface, that is now called surface charge distribution. This just means instead of a one-dimensional line, our charges are distributed over a surface. And again, we'll use rho sub s to denote uniform surface charge density. We define uniform surface charge density rho s, which is equals to q divided by the area of the surface. Okay, and if you follow similar process, we get, we get the electric field for a uniform surface charge density or surface charge distribution as 4 pi epsilon 0 integral rho s r minus r prime r minus r prime cube ds prime. And since we have ds over here, this is actually a double integral, or in other word, I can simply write a subscript s, a subscript l for the earlier one, subscript s for this current integral. Okay, so that was our second case scenario. The third scenario is when we have a volume charge distribution. Similar concept, except we now define rho sub v, which is termed as uniform volume charge distribution, which means the charges are now distributed over a volume. Let me try to draw a cube. Okay. Okay, so there is our volume. The total amount of charge distributed over the volume is Q. The volume of the surface is, or the volume of the object is V. So rho sub V will be total charge divided by the volume of the object. And following similar process, the electric field in this case will be E equals to 1 by 4 pi epsilon 0, the volume integral rho sub V r minus r prime cube dv prime. Okay, so these three formulas, we already called that one. Let's call this as 2, 3, 4. These three equations will be particularly helpful for us to determine the electric field when a continuous charge distribution is given. And when you look at equation sheet, you might see something like this. E, and it means E at some given point which has a position vector r, 1 by 4 pi epsilon 0, the volume integral rho sub v r prime r minus r prime divided by the cubed of the magnitude of r minus r prime. Okay, so notice that E is written as E being a function of the observation point and rho sub v being a function of the source point, because our charges are located at a position vector of r prime, whereas we are trying to compute the electric field at a position which has a position vector of r. Okay, so don't be confused with that notation. All right, that's it for now. We'll continue it in our later videos.